An image is worth 16 by 16 words. Transformers for image recognition at scale. Paper analysis. Abstract. The Vision Transformer or VIT is a new way of doing computer vision that challenges the usual dominance of CNNs. Instead of using convolution layers that look for patterns like edges and textures, VIT applies transformer model directly to small image patches. These patches are treated like tokens similar to word in a sentence and processed using self-attention. The big result is that VIT is trained on very large datasets such as ImageNet 21K with 14 million images or JFT 300M with over 300 million images. It can perform as well as or even better than the best CNNs. What makes this important is that VIT does this while being more efficient to train using fewer computer resources compared to deep CNNs. This shows that transformers can be a scalable and predictable architecture for vision tasks. Introduction. The introduction explains how a vision transformer fits into bigger picture of machine learning. In natural language processing NLP, transformers are already the standard model because they scale well and can be trained quickly on large datasets. Models like BERT and GPT are good examples. In computer vision, those CNNs are still most popular, with models like ResNet and EfficientNet leading the field. Some earlier attempts tried mixing attention layers into CNNs, but these were hard to scale up. The authors of this paper wanted to test if a plain transformer could handle vision tasks without using convolutions at all. Their results showed that it is possible, but only if there is enough training data. If the data is too small, CNNs still do better because they have built-in knowledge about images that help them generalize more easily. Related work. The related work section talks about past attempts to use attention for images. A simple idea was to apply self-attention directly on every pixel, but that was too expensive because of the huge number of pixels in an image. To solve this, some researchers have applied attention to small neighborhoods and tried sparse attention and combined CNN features to attention layers. Another project called Image GPT used transformers on pixels subsequences but worked only at very low resolutions. The closest attempts before VIT used very small 2x2 patches which limited to very tiny images. VIT is different because it generalizes the idea of large patches and shows that with large supervised training, a standard transformer can compete strongly with special tricks. Method. The method behind a vision transformer is actually very similar to transformers in NLP. At first, the image is cut into small, non-overlapping patches of size p by p. Each patch is flattened into a vector, then mapped into embedding of dimension d. All these embeddings form a sequence. At the start, a special class token is added. The token will later represent the whole image for classification. Since the transformer don't naturally know the order of the patches, the positional embeddings are added to keep track of the patches comes from. The whole sequence is passed through several transformer encoder layers, each made up of self-attention and feed-forward MLP blocks with residual connection and normalization. At the end, the class token is sent for a classification head that predicts the label. This approach keeps the design simple and does not add special image-based rules beyond the initial patching step. Vision transformers. The key idea of VIT is to treat an image as a sequence of patches instead as a grid of pixels processed with convolutional filters. CNNs are local filters and weight sharing to capture patterns like edges, shapes, but VAT relies fully on attention. This allows it to learn both local and global relationships of an image. The model can decide on its own whether to focus on attention or nearby across the whole image. The author also tried hybrid versions where CNNs first create feature maps, then split into patches for transformer, but the plain VAT already works very well. Another important part is fine-tuning on high-resolution images. Since the positional embeddings are tied to patch positions, the author interpolates them so the model can handle images of different sizes. This shows how flexible and general transformers are when applied to vision. Experiments. The author tested VAT on several datasets and compared it with CNNs. The model was pre-trained on three main datasets: ImageNet 1K with 1.3 million images, ImageNet 21K with 14 million images, and JFT 300M with 303 million images. After training, it was fine-tuned on tasks like Cipher 10, Cipher 100, Oxford Pets, Oxford Flowers, and VTAM. The results were clear. On small datasets like ImageNet 1K, VAT performs worse than CNNs because it does not have built-in biases. On medium datasets like ImageNet 21K, it becomes competitive. On very large datasets like 300M, it outperforms CNN. For example, VAT H14 gets 88.55 on ImageNet and 95.55 on Cipher 100. These strong results also come with efficiency. VAT needs 2 to 4 times less compute than CNNs like ResNets for the same performance. Comparison to state of art. The paper compares VAT with the best models available at the time, such as big transfer ResNets and noisy student efficient nets. These results show that vision transformers does as well or better while being simpler. For example, VIT L16 well or better for simpler. For example, VIT L16 pre-trained on JFT 300M beat L ResNet, ImageNet, and Oxford Pace while being fewer TPA core delays. The biggest model, VIT 14, performs even better, especially on harder tasks like VTAP benchmarks that includes many different types of image problems. This proves the main claim of the paper. Once trained on enough data, transformers can fully replace CNNs as the main model for vision tasks. What is striking is that VAT does not rely on complicated tricks. It uses the plain transformer encoder. Pre-trained data requirements. One of the key points of the study is that VAT really needs large datasets. On ImageNet 1K, the model struggles and often loses to smaller ResNets. On ImageNet 21K, the performance gap closes, and on JFT 300M, the VAT is clearly better. The author also tried subsets of JFT with 9 million images, 30 million images, and 90 million images. This shows that VAT tends to overfit small datasets more than CNN, but once the dataset is big enough, VAT overtakes CNN. This shows the importance of trade-off. CNNs are better while data is limited because of built-in biases. Transformers win when lots of data is available. This conclusion is that large-scale pre-training is not optional but necessary for VAT. Scaling study. The scaling study looks at how model performance changes as the size of the model and the compute budget increases. The authors compared several ResNets, VITs, and hybrid models. The result shows that VAT gives better accuracy for the same amount of compute, often needing half or quarter of the results compared to ResNets. Hybrid models which combine CNNs and VAT give small advantage at smaller scales The root advantage are larger scales where pure VITs dominate. Another interesting finding is the VITs do not stop improving within the tested range. The range that making them even bigger will continue to bring better results, like what happened with transformers in NLP. Inspecting vision transformers. The last part of the paper looks inside the models to understand what it learns. The embedding layer at the beginning learns filters that look like simple wavelets or edge detectors, which are useful for capturing details in patches. The positional embedding shows patterns that match with two-dimensional structures of image, with rows and columns being clearly related. The self-attention map shows different behaviors. Some heads focus on the whole image, even the early layers, while others look locally. As the network goes deeper, the attention span gets wider, allowing models to combine information from larger areas of image. Importantly, the attention often focuses on the meaningful part of the picture, like the main object, which shows VIT learns to balance local and global information effectively.